Okay, sorry about that. We're going to go ahead and continue on with the rest of this question. So we had already filled in part of this. I can add 2 more to find this one. And so now I'm going to use this equation that we just talked about to find how many would be in the stack if it's 10 high. So I would do 1 plus 2 times 10 minus 1. Well, 10 minus 1 is 9. 9 times 2 is 18. Plus 1 is 19. And so without having to count, the next one, 6 would be 11, 7 high would be 13, and so on. I can actually just plug these values in because I don't want to really count all the way out to what 100 would be. So I can plug this value in. So 1 plus 2 multiplied by 100 minus 1. So here I would have 99 times 2, which would be 198, plus 1 would give me 199. And so that allows me to skip the idea of that recursive pattern of just having to add 2 every time, and makes it into an equation where I can take and plug those values in. So the explicit equation is great. Now, I want us to make the connection between that arithmetic sequence and the explicit connection to the linear equation. Okay, so we're asked to write a linear function here relating the height of the stack x to the number of tiles in the stack. So we would use y equals mx plus b, or f of x is equal to mx plus b, however, and this is specifically asking for f of x to be used, so we're going to go ahead and do that. And then our slope is how much we're increasing by each time, and so since we're adding 2, our slope is going to be 2. It's 2 tiles per height, okay? And then our b is our starting point. It's going to be how many tiles we have at the beginning, and so this isn't quite the beginning. We're looking for when x is 0, so we're going to have to kind of work through that a little bit and figure that out. So here is the original formula that we had. A of n is equal to 1 plus 2 multiplied by n minus 1. Okay, and so that is our explicit equation. So what I want to do is replace the a of n with the f of x, okay, because they mean the same thing. In these past one, the a of n represented the number of tiles, and here f of x is still going to represent the number of tiles, so we're just going to replace those two things. And I'm going to replace the n with x, because here our n represented the height of the stack, and here we also want the x to represent the height of the stack. So I'm just going to replace these and make it f of x is equal to 1 plus 2 multiplied by x minus 1. Okay, just getting all of our variables to match. Now, then the next step, if I wanted to get this into slope-intercept form, I could simplify this. So f of x is equal to 1 plus, and I would distribute to do that, 2x minus 2. Okay, I can distribute that, and then I can just simplify by adding these two things together. So f of x is equal to 2x minus 1. And so that becomes now my equation, and I can see that my slope was 2, and it turns out that my y-intercept was -1, which makes sense, because if I were working backwards, going from 3 to 1, I'd be subtracting 2, and going from 1 to 0 height, I would subtract 2 again, and 1 minus 2 would be -1. So this equation, this a of n is equal to 1 plus 2 multiplied by n minus 1, this explicit equation is the same as this linear function written as 2x minus 1. They're the same thing. And so that's kind of this relationship that I want you to be able to see. So I'm going to do another example, work it all the way through so that we can see this happen again. Okay, so let's look at number 3. Lucy has $3.75 in her piggy bank before school starts. Her mom gives her $4 for lunch each day, but lunch only costs $3.25, and her mom doesn't ask for change. So she decides that she will put the change in her piggy bank each day. So the table below shows this relationship. So on the first day of school, she has $4.50 in her account, in her bank. Then she has $5.25. Then she has $6. Then she has $6.75. So if we continue this pattern, okay, you'll notice she is adding 75 cents each day, which is the change that she's getting from her mom's lunch that she's paying for. So the next one, if we added 75 cents again, we would have $7.50. and if we added 75 cents again, we would have $8.25, okay, and so on. So to describe the recursive pattern, we're adding 75 cents each day. Okay, that's kind of the pattern here. The explicit equation, we would have our difference, our common difference, the change that's happening each time would be plus 75 cents. Okay, and then our starting point, that first day, would be $4.50. So we can plug those values in. A of n is equal to $4.50 plus 0.75 multiplied by n minus 1. And that becomes our explicit equation. Okay, so we easily found that 5 was $7.50 and 6 days was $8.25, but I don't really want to keep adding that way in order to find how much money she has after 14 days and after 100 days. So I can use our equation that we just created in order to plug those values in. So we want to look for n being the number of days. I want to know what happens when there's 14 days involved, okay? So I can plug that value in. 4.5 plus 0.75 multiplied by 14 minus 1. So we do a quick calculation on that. 13 multiplied by 0.75 plus the 450 becomes $14.25. Same thing over here. We do 4.5 plus 0.75 multiplied by 100 minus 1. So it's 99 multiplied by 0.75 plus the $4.50. And after 100 days, she's got $78.75 in her account. Okay, and so that allows us to not have to, this explicit equation allows us not to just say, okay, all right, I got to get from 14 days to 100 days, so I've got to add 0.75, 76 more times, or 86 more times. So that keeps us from having to do that. Okay. And then the last question here asks us to write that linear function that relates the number of days, x, to the amount of money in the bank. So previously we had this being n, and the money in the bank was a of n, and that's what we were using. So now it's asking us to relate the number of days as x, and the money in the bank to be f of x. So we're going to rewrite these. So I'm going to take this equation. That's a of n is equal to 4.5 plus 0.75 multiplied by n minus 1, and I'm going to change out the a of n for f of x, and I'm going to replace the n for x. All I'm doing is just replacing those to make it clear. Okay. Then I'm going to simplify this because I want it to be written as a linear function, and we know that linear functions are generally written in that slope-intercept form, or f of x is equal to mx plus b. So that's the format I'm going to try to get this in. So I'm going to simplify. I'm going to distribute. So f of x is equal to 4.5 plus 0.75 x minus 0.75. We're going to add these two things together. So f of x is equal to 0.75 plus 3.75. Okay? And so this becomes our equation. And so this time our m is our slope, 7.5, which is the same as our difference, as it should be, because that's how much it's increasing by each day. But our b value is 3.75. It's different than the first term. And I guess that throws a lot of students off, but the truth of the matter is it's different for a reason, because day one she had $4.50 in her bank. But before that, before day one, she had $3.75 in her piggy bank. That was before she put the first amount of money in there. So her initial amount in the piggy bank was $3.75. The first day she had the $4.50. So when we're looking for the first term of the pattern, we use that $4.50 because that was the first amount that she put in. Whereas here, when we're looking for our y-intercept, where x is 0, before she ever put money in, the initial value was $3.75. We have to back up one more term in our pattern. And so I want you to be able to see that difference between that explicit equation and that linear function.